As a programmer, you've likely had to deal with storing user authentication information at some point in your career. You heard that encryption is bad, hashing is good, so you decided to dig in. You ended up on Programmer's Fight Club, reading up on answers given to those unfortunate souls brave enough to ask questions there. You allow yourself a brief moment of fun, seeing other souls get tortured, and then copy-paste the code you need and sneak away. Yes, of course, I'm speaking from experience. Ultimately, you learn that you should just use Bcrypt because it's an industry standard, used by just about every authentication library and service in existence, including Auth0, so you plug it in, and you feel rad. You've done your job well. You also learn that you should never use the SHA family of hashing algorithms, and that you should especially avoid MD5. If you're like me, you think to yourself, I should probably understand why, but then you move on because you have work to do. Then you get an email from Troy Hunt because your company email has been found in a data breach, and at the same time, your boss lets you know that there was an incident over the weekend and asks you about the security of sensitive user data. Hey, you just lost your database. Then you get pulled into a triage meeting where you're asked about your security measures, specifically how user passwords are stored. You respond that, well, I used Bcrypt, and then you quickly realize that it might have been a good idea to understand more about hashing algorithms because the questions, now they're going to get kind of intense and detailed real fast. No worries, friendo. Let's do this. Let's dig in. Let's figure this out. Start the timer. This is hashing in 60 seconds. A hash is produced by a hashing algorithm. It's a unique signature for a set of binary values. A usable hashing algorithm has 4 distinct traits. They need to be deterministic, which means you can nice, Rob. You can rerun the same algorithm over the same data and you'll get the exact same result. They need to be one-way or asymmetric, meaning there is literally no way to decrypt them. And they need to produce a globally unique value across all space and time for a given bit of data. This is called collision-free. No 2 distinct binary values can have the same hash. This is why people don't use MD5 anymore, as it's been shown to collide under certain conditions, which is bad. They also need to be volatilely random, say that 10 times, which means that the smallest change to the input data creates a completely different hash. Changing the output value from high to ho, as in ho-ho-ho, produces a completely different hash with just a single letter change. And finally, for most use cases, a hashing algorithm should be fast. Most use cases that don't involve hashing sensitive information, like a password. This is the main reason why This is the main reason why people don't use the SHA family of hashing algorithms for password storage. They're just too damn fast. All right, that's my 60 seconds. I don't know, I didn't time it. Whatever, who cares? Let's move on. Why is speed or not speed important, you ask? When you lose your data in a breach, the perpetrator will likely run a brute force attack on your sensitive information, including passwords. Looking at this data here, I can immediately see that the hashed password data was produced by version 2A of the Blowfish cipher using 10 rounds of salt. It's trivial, as you'll see in a moment, to put each of these passwords under a brute force attack with the goal of guessing what the hash is. They do this by using a thing called a rainbow table, which is a massive set of pre-computed hashes created from passwords that were stolen from other sad souls. We're using Bcrypt, so we have some protection against this, and you'll see why in a second. But if we're using SHA-256 to hash our users' passwords, we'd be in big trouble. To understand this, consider that there will be a user of yours who has something like password123 as their password, something silly, bypassing your password rules. Damn them. You can hash this using SHA-256, then Google that hash value, and, well, you're going to see how quick and simple it is to guess this password. Yes, you're going to see password123, just like you see right here on the screen. This type of attack is called a pre-imaging attack, and it's the one that we care about the most when it comes to hashing and storing our passwords. It's worth knowing that these pre-imaging attacks aren't really all that sophisticated and are enabled by the use of a thing called a rainbow table, which is just a set of pre-hashed values of common passwords and words and other things scraped and broken from data breaches in the past. Now, there is a way to thwart a pre-imaging attack, and let's see what that is with some code. Here, I'm using Node with its built-in crypto library, and I'm hashing our amazing password, password123. Running this in VS Code's terminal, and we can see the output. And if you Google this, you'll see password123 come up real quick. That's not good. So let's add some countermeasures. Here I'm adding what's called a salt, a random string appended to our password, or you could prepend it, whatever you want to do. We then use the salted value to generate our password hash. Running this code, and you can see that we have a completely different hash, which you wouldn't find in Google, which is great. When it comes to verifying this, we simply append our salt to the passed-in value that we want to verify against, then we hash that, and then compare what's stored in our database. This is fine and all, but if you lost your database, you probably also lost your hash, which means you accomplished pretty much nothing. An attacker will just use the salt value in their attack. Also, it's never a good idea to use a global salt like I'm doing here, so just forget you saw this. What you really want to do is to create a salt per password and then attach that salt to the salted hash itself. This might seem counterintuitive. We're giving up the salt. What gives? That seems like a really bad idea, but it turns out that it's not. The salt doesn't need to be secret at all. That's not its purpose. Its purpose is much simpler. We are forcing our attacker to run a pre-imaging attack on each password individually, instead of the entire table at once. That's clever, don't you think? This brings me to more modern solutions like Bcrypt and Scrypt and how they offer even more countermeasures. Like I said, don't use SHA-256, even though I just did here, so forget you saw that. Bcrypt automatically adds a random 16-bit salt to each value it hashes, but it creates that salt using what are called rounds. If you don't give it a salt, it'll make one for you. The more rounds, the slower the salt calculation, and the more frustrated our attacker gets because they have to calculate that salt with every single guess they make. Slow countermeasures work, but the bad guys have gotten very smart and have specialized hardware just for this kind of thing. Slow hashing algorithm? No worries, we're going to spread that workload over 100 or so graphics card processors. So how do we fight these guys? Well, let's answer that using Bcrypt. To use Bcrypt in a Node application, you need to install a separate library, either Bcrypt or Bcrypt.js. Here I'm using Bcrypt.js because there's no dependencies on native code. I'm also using an asynchronous function because I want to be sure that this is non-blocking. Remember, we have to use CPU for this. If you use blocking code, you're going to block everything. In fact, that's where Bcrypt shines, generating that salt. Tuning the rounds is exponential, so 12 rounds is exponentially higher and therefore slower than 10. Security people suggest tuning this as high as it'll go before it pisses off your users, which I found to be just about 12. Let's see this in action. I'm going to run our hashing algorithm over a set of random values and start out with 10 rounds of salt. Yeah, that's pretty quick. I'll up it to 11, and you can see that it's noticeably slower. Let's push that to 12, and we get an average of about 270 milliseconds and change. That's actually still kind of fast. 13 takes about a half second. This seems like it's a very bad thing. As programmers, we like things to be fast, but you have to consider that a user will only encounter this when they register and log in. Bcrypt has been around for a while, and security types are gently urging developers to use more modern hashing algorithms because in the crypto world, you want an algorithm to be around long enough to be respected, but not so long that people have figured out ways to break it. The first one we're going to look at is PBKDF2, which has been around for a while. There's a little extra work that you have to do in using it, namely that you have to be sure you manually store the salt with the hash. Either append it as I'm doing here, or in a separate column in your database. The nice thing is that you can tune the hash calculation rounds as opposed to just the salt, as well as the length of the key. Here I've set the rounds to about 1 million and a key length of 56, making the hash calculation nice and slow. This flexibility is a good thing, but unfortunately it only taxes the CPU because it uses the SHA algorithms under the hood. Why is that a bad thing? Because the bad guys also use GPUs, as I mentioned. These are extremely fast, especially when used in parallel, mitigating your CPU clogging defenses. This means that PBKDF2's defensive measures are out the window if your attacker is using an array of GPUs. But what about Bcrypt? Does it have the same problem? It turns out it doesn't. To defeat the GPU brigades out there, hashing algorithms like Bcrypt and Scrypt, which we'll see in a second, use a lot of RAM during the hash computation process, which GPUs can't be optimized for, especially in parallel tasks. This is called memory hardness when an algorithm requires a bunch of RAM. As a programmer, you can think of this using Big O. GPUs are good at time complexity, but not space complexity. All right, well, this is Scrypt, as I mentioned, and is once again usable with Node's built-in crypto library. It's been around since about 2009, so it's relatively new, which makes people shy away from it a little bit, as it hasn't been battle-tested like Bcrypt, but it's getting there. Things look very much the same here code-wise when compared to PBKDF2. I need to use a promise so I don't block things, but as you can see, I have an additional parameter that I can send in, and that's the cost. Here, I'm setting the cost to 2 to the 14th, the highest I can set. This will ramp up the RAM required in the hashing calculation into the megabytes. Bcrypt is in the kilobytes, which is easy for the CPU of a PC, but very hard on a GPU. The similarity of Bcrypt and Scrypt has led to a lively debate in the crypto world. They both work and do a good job, but only time can tell if attackers can optimize their hardware in one way or another to thwart Scrypt, which seems to be its main criticism. We just don't know if it's good until it's lasted the test of time. The last algorithm that we get to play with today is my favorite. It's Argon 2, and to me, it is the most interesting, capable, and compelling hashing algorithm that I've seen in my limited research. To hash a password with Argon 2 using Node, you need to install the Argon 2 library and call a simple hash method. This is where things get truly interesting. You can pass options to fine-tune how much RAM it will take to create the hash, the length of the hash, how much CPU time it'll take, and finally, this is bonkers, how many threads are required to run in parallel in order to run the algorithm. There is nothing you need to do regarding salt storage. That's handled for you, and as such, verification is a very simple matter. Like Bcrypt, Argon 2 stores meta information in a $ delimited string as part of the hash. Here we can see that Argon 2i was the algorithm, version 19, the memory cost M, the time cost is 20, parallelism is 5. The next value is the random salt string, and the final value is the actual hash. One of the articles I read as I was researching this subject over the past few years is a brilliant deep dive from so-called security fanatic Michelle Precioso. I didn't murder your name, sorry if I did, which agrees with a lot of what I've read online. People really dig Argon 2 and the protections it provides. It's a newer hashing algorithm and will be an interesting one to watch for sure. So if I had to go on a limb and suggest an algorithm for you, I would say to give Argon 2 a try. It's super easy to use, it's very compelling. Otherwise, both Bcrypt and Scrypt will get the job done, with Scrypt being a little bit more resilient against GPU attacks. I'm certainly not a crypto expert, so if you've spotted any issues or have a disagreement, do let me know, pop them in the comments, and I'll try and read it someday. I'm hoping to do a lot more of these videos, and if you've learned something, you can support my efforts by heading over to bigmachine.io, where I sell books and videos for developers just like you, including The Imposter's Handbook, which is a book I wrote a few years back for programmers like me who don't have a CS degree. Thanks so much for watching, I'll see you again.